it's time for us to do some problems involving Newton's method. And as always, it's important that you do as much as you can on your own. If you're following along with this video, consider making frequent use of that pause button. And pause and try to first do it by yourself. And then you can unpause and see what I did. And of course, we can compare. Hopefully, we get the same answer. And the more that you do, the better you're going to get. And you're going to become amazing. Okay, well, let's begin. Our first problem says, use Newton's method to approximate the square root of 2, starting with x equals 1. Now, we know we're going to use Newton's method on this problem, and our clue is it says, use Newton's method. Pretty good clue. In fact, it's one of the best clues. But you might say, there's something missing here. Where's the function? You see, Newton's method does what? Newton's method says, I want to say there's some function f of x set equal to 0, and my goal is to get a good approximation to that x where it's true. There's no f of x given here. So how do we apply it? Well, this is a case where we have to give the function f of x. So now we say to ourselves, all right, what's our real goal? Our real goal initially is to say, I want to find some function where when I plug root 2 into my function, the outcome is 0. So we start thinking about, well, what's a function that does that? Now you might say, I have a function. Here's a great function. X minus root 2 does that, right? If I know, if I plug in root 2 into the function here, right? So here's my function. Root 2 minus root 2 is 0. Life is good. Aha! We've solved it. We're ready to go. Well, hold on. We can't do that, though. Now you might say, why not? Doesn't it work? Well, in some sense, yes, but in a more important sense, no. So what's the more important sense? You see, in order for us to use this, we would have to know what square root of 2 is. Now the catch is, if we knew what square root of 2 is, we wouldn't have to go and approximate square root of 2. And therefore, this is not a good choice, because really it involves our answer. So no, this won't work. It involves a number that we really don't have a handle on, which is namely that square root of 2. Okay, but there's another function we can think of that would work. You can even think about what's true. The thing is, if you take the square root of 2 and you square it, you get 2. So we could say, aha, I could think of this, say, my function as being x squared minus 2, right? Because if you plug square root of 2 into there, you'll get 2 minus 2, which is 0. And that does work. That's good. Because 2, we know. At least we think we do. Well enough anyways. Okay, so now we have our function. We also have our initial guess. So we have our two important things. So we start saying, okay, what does Newton's method say? And it's a good thing to always start by writing down the formula. Newton's method would say the following. Our next guess is found by taking our current guess and subtracting off a term. And this is, you can think of this as sort of a correction term. You say, well, look, our current guess isn't right. Here's a piece that gets you closer to it if you modify your current guess in that way. So in our case, our function, we're going to use this function here. Okay, well, that would say we have xn subtract xn squared minus 2. Now, what's the derivative of x squared? Well, we should probably make a little side note there. The derivative of x squared minus 2 is 2x. All right, so there's our derivative. Good. So our f prime of xn, and what does it mean to say f prime of xn? It really just says plug xn in. So where you see an x, you put xn, 2xn. Now, that's correct. Well, let's clean it up. Let's make it look nice. All right, so what do we do? Well, that would be xn minus, and we'll take xn squared, divide that by 2xn, and then minus minus makes a plus, 2 divided by 2xn, and we say, aha, we can do some things. We can cancel some 2's, And we can cancel some of xn's in this middle term. Da, da. All right. So, a little bit more we can do. See, that's an xn, and that's subtracting xn over 2. So, if we put that together, we end up with xn over 2 plus, and the last term is 1 over xn. So it says the rule is actually very simple. You take your current guess, divide it by 2, add to that the reciprocal of your current guess, and that gives you your next guess. Okay, well, let's do this. And so we begin. X0 equals 1. All right, that's good. Now, our next guess, x1. 1 over 2 plus 1 over 1. So 1 over 2 plus 1 over 1, well, that's not so hard to compute. That's 3/2, which is 1.5. All right, that's better. It's better than 1. Probably not great. We'll get better still. Okay, how about x2? So the rule is take the current guess, divide by 2. So that would be 3/4. Add to that the reciprocal of the current guess. So flip it over, 2/3. Well, here we see common denominator is 12. Then we'd have to multiply the first term by 3. That would give us 3 times 3 is 9. And then 4 times 2 is 8. And 9 plus 8 makes 17. 17/12. Now, if you use a calculator, and I did, you can find that this is 1.41666 ... A better approximation, we think. We'll talk about what the square root of 2 is in just a second. All right, let's go one more. Why not? What would x3 be? Well, current guess divided by 2, that would be 17 over 24, plus, take the current guess and flip it over, 12 over 17. Now, 24 times 17, well, 20 times 17, that's not so bad. 2 times 17 is 34. Then add a 0, 340. 4 times 17 is 68. So that would give you 408. Now, what's the numerator? 17 times 17, well, it's 289. And 12 times 24, well, that's 2 times 12 squared. 12 squared is 144, so 2 times that is 288. Wait a second, hold on. 288 and 289, they're really close to each other, right? In fact, they are very close to each other. We'll talk about that in just a second here. So if you add 288 plus 289, you get 567. And you put that into your calculator. What do you get? 1.414215.6. So forth and so on. Okay, now, that's 3 steps. How are we doing? Well, let's talk about what the square root of 2 is. So what's the value for the square root of 2? Well, it turns out that square root of 2 starts off as 1.414213, so forth and so on. So you'll notice we've already gotten a reasonable approximation. Not so bad. Not so bad. Of course, you might say, well, we could do better. Of course we could. We could do better. But for only taking this procedure and applying it 3 times, we've already gone all the way to 5 digits past the decimal point as far as how correct we are. Now, suppose you wanted to go further. What would the next term be? Well, okay, I will tell you that the next term, we'll just go ahead and skip the intermediate steps. 665,857, divide that by 470,832, and what is that? Well, that's 1.414213.5. So far so good. In fact, it keeps going. 6, 2, 3, 7, 4, 6, and it is correct all the way up to the 7. That's how accurate it is. So in other words, it agrees with square root of 2 up through that many digits. All right. Now, I will say that probably most people, in terms of practical computation, would not want to work with that number. They would much rather work with something like 567 over 408. Maybe they wouldn't even want to work with that. Well, that's possible. That's possible. Now, I want to point out something we've talked about in sort of passing and say, hey, let's think about this. Namely, looking at 17 over 12. Well, 17 squared was 289, and 2 times 12 squared is 288. Now, the fact that these numbers are so close to each other is reflected in the fact that we're a good approximation to root 2. If they had been exactly equal to each other, we would have found the exact value for square root of 2. And so, generally speaking, we just want those to be very close. We can actually see the same pattern holds. So look at that. 3 squared, what is that? 3 squared is 9. And 2 times 2 squared is 8. Again, close, off by 1 digit. How about here? Well, whoops. That's a typo. It's not 567. It's 577. Oh, my goodness, I'm sorry. Because 288 plus 289, see, that'd be 560 plus 17, which is 577. My apologies. But that's the correct decimal approximation. Okay, so how about that? Well, if you were to multiply and expand this out, you'd have 577 squared. Okay, don't worry, I wrote it down. So that is 332,929. And 2 times 408 squared is 332,928. And so, again, they're just off by 1. And it's this closeness. Essentially what's happening is this procedure is finding the ratio of two numbers where the top number squared versus double the bottom number squared are off by just 1. And that's why we're going to keep finding things which are getting better and better approximation to the square root of 2. Now, you might wonder, wow, this is amazing. When was this discovered? Well, the answer is a long, long, long time ago. This predates Newton by a couple thousand years. People have been really interested in numbers like square root of 2 and trying to find ways to compute it. And so, yeah, this goes back to the Babylonians. They were able to do computations like this. And it was a nice way to pass the day. You know, this was before Xbox, so they needed something to do to spend their time. So they're like, well, let's get a really good approximation to square root of 2. And they got some really good approximations. All right, good. Fun stuff. All right, let's do another problem. Use Newton's method to approximate a root to y equals x cubed plus 7x minus 3, starting with x0 equals 2. Give the exact value to x3. All right, good. Well, now it's very straightforward. We know we're using Newton's method. We know what our function is. Namely, it's this x cubed plus 7x minus 3. And we know our initial guess. So our life is fantastic here. So let's start by writing down sort of the mechanism, the machinery that we need for Newton's method. So that says to get our next guess, we take our current guess and subtract the function at our current guess divided by the derivative at our current guess. And we'll write down our function and our derivative for reference. So the function, x cubed plus 7x minus 3, and the derivative, that's not so hard to compute. That's 3xn squared plus 7. All right. So here we go. That would be xn. Now, I'm going to take our function and replace all the x's by xn's. So xn cubed plus 7xn minus 3. Divide that by, downstairs, 3xn squared plus 7. All right, now we have our expression. From here we could start. In fact, you wouldn't get the wrong answer if you started here. But sometimes it helps to clean up the expression first, because you might get some simplification, you might also get some cancellation. You don't have to, but just to sort of demonstrate the philosophy, let's go ahead and carry this out. So what do we mean by clean up? Well, let's add these two together. So I'm going to multiply this xn by 3xn squared plus 7 over 3xn squared plus 7 so I can combine. So we would have 3xn cubed plus 7xn, and then minus xn cubed plus 7xn minus 3, and all that divided by 3xn squared plus 7. And now you might say, oh, there is some cancellation. You see, the more cancellation you can do now in setting up the rule says you can save yourself from having to keep doing cancellation later on. And so that's why it's nice to get your rule in a very nice, simple format. The simpler it is, the easier it is for you in the next step when you go about actually carrying out the computation. So we have 3xn cubed subtract xn cubed would leave us with 2xn cubed minus minus makes a plus 3, and then divide it by 3xn squared plus 7. All right, so there's our rule. It's actually pretty simple now. And so simple, we can do it. All right, so next step, do it. We begin. We know what x0 is. We're told x0 equals 2. So to get our next guess, see, this is our 0th guess, so we can think of x1 as being our first improved guess. So how do you get x1? Well, we're going to take this 2 and plug it into our expression. So it'd be 2 times 2 cubed plus 3, divide that by 3 times 2 squared plus 7. Now, you could just leave it as this, but probably not the smart thing to do. You see, you want to have a simple expression to work with. And so if you're going to keep doing something, you should continue to simplify as you go along. Only when you get to a point where it's like, I'm not going to do anything else with it, that's the point where you say, let me not bother with simplifying because, I'm not doing anything else with it. So, let's see. 2 cubed is 8 times 2 is 16 plus 3 is 19. Oh, dear. 3 times 2 squared is 3 times 4 is 12 plus 7 is, also 19. 1. Woohoo! Yeah! Worked out nice. Okay, good. Now, x2. You see how much easier it is to plug 1 into this expression than to plug this thing into there? So much easier. Okay, so we plug in 1. So we have what? 2 times 1 cubed plus 3 over 3 times 1 squared plus 7. Well, that's 2 plus 3 is 5. 3 plus 7, 10. 5 tenths, also known as a half. All right, good, nice. Now, last one, right? Because we only had to go to x3. Okay, so 2 times 1/2 cubed plus 3. Divide that by 3 times 1/2 squared plus 7. Now, can we stop? We actually can't. This is a correct answer. In other words, it is the exact value to x3. It just hasn't been simplified. Now you might say, do we have to simplify? This is a great question. A lot of students ask this question, and the answer is, well, it depends what they want you to do. Now, suppose we did want to simplify. What would we do? Well, I see that there's a halves here, which means there's fractions within fractions. I'd want to get rid of it. I can do a little something here and notice, well, see how I have a 2 and then a half? I can cancel one of my halves. So really this is like a 4th plus 3. Here I have 3/4 plus 7. So an idea would be, let's multiply top and bottom by 4. That would get rid of our fractions. So what do we have? Well, a 4th times 4 is 1. 3 times 4 is 12. Downstairs, 3 times a 4th times 4 is 3. 4 times 7 is 28. So we end up with 1 plus 12, which is 13. 3 plus 28, which is 31. So 13 over 31. It's also the exact value. It's just written in a more simplified form. It just depends on what's being looked for. What are we looking for? What's the right way to write it? All right, good. Let's try another problem. Okay, so use Newton's method to approximate a root of f of x, which is x to the fifth plus 3x squared minus 9x plus 9, starting with x0 equals 0. Okay, and it says also start with x0 equals negative 2. You're allowed to start in multiple places, and sometimes you say, oh, if I start in one place, it doesn't work out so well, start somewhere else. That's not an unreasonable thing to do. All right, so we have our function. So let's write down our generic formula. We have our xn plus 1. Our next guess is our current guess, xn. Subtract the function at xn, divide by the derivative of the function at xn. Our function here, that's x to the fifth plus 3x squared minus 9x plus 9. So taking the derivative, we would have 5x to the fourth plus 12x minus 9. Whoops, not minus 12x. Minus 6x. Sorry. There we go. Now it'll be like nobody even noticed. Right? The 2 comes down. Okay. There we go. There we go. All right. Well, let's figure this out. So we have, this is xn minus, okay, then we have to plug this in, xn to the fifth plus 3 times xn squared minus 9x9, sorry, minus 9xn plus 9. Okay, divide that by 5xn to the fourth plus 6xn minus 9. Good. Done. Good. Now, what do we do next? Well, one thing we can do, of course, is we can simplify this expression. And, I mean, I like simplifying. Let's go ahead and do that. So, if we simplified it, what would we get? Well, we would have 5xn to the fifth plus 6xn squared minus 9xn, subtract xn to the fifth plus 3xn squared minus 9xn plus 9, all over 5xn to the fourth plus 6xn minus 9. Okay, so far so good. And we say, so far really good, because we get some cancellation. And of course we can combine. So we end up with 4xn to the fifth, 5 minus 1, 6 minus 3, plus 3xn squared, and a minus 9 on the end. Divide that by 5xn to the fourth, plus 6xn minus 9. Okay, so that's our rule. There we go. There we go. All right, so let's start with x0 equals 0 and see what happens. Well, plug in x0 equals 0. Now we plug 0 into here. It's really easy to plug 0 in, right? Because 0, 0, 0, 0, minus 9 over minus 9 would simplify to give us 1. Cool. All right. So now, how do we get our next guess? x2. Well, plug in 1. 4 plus 3 minus 9 is negative 2. 5 plus 6 minus 9. That's 11 minus 9 is positive 2, which gets us to negative 1. Oh, that's nice. Okay, so now plug in negative 1. Okay, negative 1 to the fifth is minus 1. Negative 1 squared is plus 1. So we get minus 4 plus 3 minus 9. So what does that end up being? Well, it ends up being negative 10. Downstairs, we'll get minus 1 to the fourth is a plus 1. Minus 1 is a minus 1. So it's plus 5 minus 6 minus 9. What is that going to end up being? Well, it's going to end up being negative 10, which is what? It's 1. They might say, uh-oh, You've seen it before, right? Well, what is that going to say? Well, it says the next answer is going to be -1. And the answer to that is going to be +1. And so forth and so on. It's going to get into a vicious cycle. And that can happen. You see, what can happen is it's the case where some functions, when you look at the root and you have guesses, well, one guess will shoot you over to there, and then this guess will say it'll shoot you right back to where you start. And so it's going to have your guesses jump back and forth and back and forth and back and forth. See, it never matters how many times we apply this rule. We're never going to get close because we're always going to be alternating back and forth. So this is not going to get us what we want. What was our problem? Well, our problem was we had a bad initial guess. We probably should have probed a little bit around and tried to get closer to our initial guess. So that's why it says, hey, try a different initial guess. So for example, if you start instead of at 0, you start at -2, well, what happens with there? Well, hopefully we get better answers. Well, what would x1 be? Let's see. -2 to the 5th. Well, 2 to the 5th would be 32, and then the negative will make it negative. Times it by 4, that's -128. Ugh. -2 squared, well, that's 4 times 3 is 12, so plus 12 minus 9. Downstairs, -2 to the 4th is 16 times 5 is 80, and minus 12 minus 9. And, okay, well, I don't know. Does it simplify? What do we have? Well, if we have 128 plus 12 minus 9. See, the plus 12 minus 9 is really like we're adding 3. So that's really -125. And subtract 12, subtract 9 is like we're really subtracting 21. If you take 80, subtract 21, that's 59, right? So, okay, there's the next guess. And ... At this point, this is like, you really want to use a calculator here. So, but the point is, if you were to keep going here, you would not be stuck into a cycle. You'd be able to break out of the cycle. And it's good to be able to break out of that cycle. Okay, so continue this on your own and see how you do. All right. Time for another problem. Of course. Okay. So for the function f of x equals x cubed plus 2x plus 2, using Newton's method starting with x here equals 2, find the exact value for x4. All right. That's a large number, x4. Now, let me just put a little bit of a warning here. Almost always, if you start with a random polynomial and a random initial guess, after about 2 steps, the number is going to be very unwieldy. It's going to be a fraction, and you're like, ah! So, whenever you see something that says, oh, find the exact value for x3 or x4, what that means is that they have been carefully selected, groomed, chosen among tens of thousands of possible choices so that things work out nicely. So, I suspect things are going to work out nicely here. Don't expect things to always work out nicely. I just want you to be aware of that. So if you're like, man, these problems just don't work out as nice as the ones that were done in the practice, there's a reason for that. All right, so here we go. We'll write down our basic formula, xn plus 1. That's xn minus f of xn over f prime of xn. So, well, that's xn minus, and upstairs I'll do xn cubed plus 2xn plus 2, and downstairs I'll not start to take the derivative. Derivative of x cubed is 3x squared, so that would be 3xn squared, and then plus 2. Now I've always been simplifying, so just for this one we won't simplify, just so you can see it doesn't really matter. All right, now I have the rule. The rule is ready to go. So we start. x0 equals 2. All right, how about x1? Well, that's going to be 2, because I put my current guess here, subtract. Now I'm going to plug 2 into the function. So 8 plus 2 times 2 is 4 plus 2. So 8 plus 4 plus 2 makes 14. 3 times 2 squared, that's 3 times 4, that's 12 plus 2 is also 14. So you get 2 minus 14 fourteenths, which is really 2 minus 1, which is 1. Nice. Okay. Now, x2, our next guess. We take our current guess, plug it in, so there, put a 1 there, subtract. Now we put 1 here. So, nice thing about 1 is it's really easy to compute 1 to any power is 1. So we get 1 plus 2 plus 2. So that would be 5 downstairs. 3 plus 2 is 5. 1 minus 5 fifths, also known as 1 minus 1, which is 0. Nice. Okay. How about x3? Okay. Well, 0 is also fun. See, so we're going to take 0, plug it in, so that's 0, minus, we have 0, 0, 2, and here we have 0 and 2. So it's really 0 minus 2 over 2, which is negative 1. Okay, so we went 2, 1, 0, minus 1. It's like we're sort of working our way down. So you're probably thinking, aha, I see the pattern. What do you think the next one is going to be? Nope, it's not that. It's not going to be negative 2. Okay, what is the next one? In fact, it's the last one. And probably that's a sign that after this point, it gets messy. Okay, so what is x for? The answer. So that's plug in negative 1, subtract. Okay, negative 1 cubed is minus 1, then minus 2, and plus 2. And then downstairs, 3 times minus 1 squared, well, that's 3, and then plus 2. All right, the 2's and minus 2's cancel. The minus and the minus cancel. So it's really minus 1 plus a fifth, 4 fifths. All right. Oops, minus 4 fifths. There we go. It probably is a sign, by the way. You see how we kept sort of moving, doing, and then all of a sudden from negative 1, not as much movement. It probably means that we're close to where the root is at. And if we were to keep going, and at this point, this is when you'd really want a calculator to come into play. But if you were able to keep going, you'd say, we're really close. We really are getting close to our answer. Good. Good. Well, let's do another problem. Use Newton's method, starting with x0 equals 2, to get an estimate for a solution of x cubed equals 5 plus 5x. Give the value for x2. So we're going to have to do 2 steps. But you might want to say, wait a second, hold on. How is this Newton's method? Because what's going on here? Well, what's going on here is you have these 2 curves. You have the x cubed curve, and if you were to sketch that, what does that look like? Well, we have a pretty good idea of what x cubed looks like. It looks something like this. And then we have another curve called 5 plus 5x. And what does that look like? Well, that's a line. And if you were to sketch it, it would look something like that. And what are we after? Well, we're after a root. Okay, now it looks like there's going to be multiple roots. And sorry, we're not after a root, we're after a solution. We're looking for where they cross. We're looking for where they intersect. So it looks like there's multiple times where they intersect. And so we just want to find one of them. We'd be satisfied if we could find one. The problem is these aren't roots in our traditional sense, right? Because roots are where we cross the axis. And so how do we transform the question that's asked to one that we can use Newton's method on? Well, the idea here is very simple. It says, look, Newton's method is about saying, I want to know when something is equal to 0. So if I want to know when 2 things are equal, what that really says is I can figure that out by looking at a function which consists of their difference. So I'm going to take x cubed subtract 5 plus 5x. So if I know the root of that expression, that would be a time when these 2 cross. So that's how we use Newton's method to do a problem or we say when do two expressions equal one another. Okay, well, let's work this through. So we have xn plus 1 would equal xn, subtract, in the numerator, x cubed, and I'll go ahead and distribute that minus through. And I'll put it as minus 5x minus 5. And then take the derivative, and then there's little n's attached to the x's. The derivative of this would, well, the derivative of x cubed is 3x squared, so I get 3xn squared. The derivative of the 5 is 0. The derivative of 5x, or really minus 5x, is just minus 5. Okay, so there's our rule. So now we're most of the way there. Okay, so we won't simplify this time. Let's plug in and see where we go. We know what x0 is. x0 is 2. How about x1? So that would be 2. So we're plugging the 2 into here. Subtract. Plug 2 in. 2 cubed is 8. Then minus 5 times 2, so that's minus 10. Minus 5. Downstairs. 3 times 2 squared. That's 3 times 4 is 12. And then minus 5. Okay. 8 minus 10 minus 5. Well, that's really 8 minus 15 is negative 7. So this is really 2 minus negative 7. And then 12 minus 5 is positive 7. So minus makes a plus, and 7 over 7 equals 1. So this is 3. Ah, nice, nice. Again, we have chosen these problems carefully so that the numbers are nice. Do not expect numbers to always be nice. Sometimes life is not always nice. But your calculus teachers are, because they love you. We love our students. You're so great. And we love you to, I don't want to say we love you to death, but boy, we really want you to succeed. Okay, all right, back to our problem, right? Okay, we're so close. We just need to do x2 now. So what is x2? We're going to plug 3 in. So 3, subtract, upstairs, we would have 3 cubed, then minus 5 times 3, 15, minus 5. Okay, downstairs, 3 times 3 squared, minus 5. All right. We could stop there, or we could do a little bit of simplifying. Let's try out a little bit of simplifying. And if it looks too bad, we'll stop the simplifying. But fingers crossed, maybe it's not so bad. Maybe. All right, so 3 cubed is 27, and then we're really subtracting off 20. So the numerator here will simplify to be 7. And let's see, 3 times 3 squared is really 3 cubed again. That's still 27. And subtract 5 would give us 22. So what do we have? Well, we could say 3 times 22, that's 66 over 22, and then we subtract 7, and 66 subtract 7 would give us a 59. 59 20-seconds. All right. Good. Now we have a good idea why they said, give us what x2 is, because x3 would probably not be a nice number. There's no common terms between 59 and 22. All right. But the real moral for this problem is when you have two functions being equal to each other, it's the same as saying, take their difference and set it equal to 0. Now, Newton's method, go. And success. Or at least approximation to a success, right? That's what we're after. Good approximations. All right. One more problem. When xn plus 1 equals 4xn over 5 plus 4 over xn to the 4th, and x equals 137, which is just sort of some random number, then the xn approach a particular value as n gets large. So in other words, we keep applying this rule over and over again, and all of a sudden, in the long run, probably not very long, we say, oh, there's this particular number that starts to come out. And the question is, what's the number? Okay. Now, we'll do two ways to do this problem, even though, yes, only one way would suffice. And they're both sort of nice ways to think about things. Okay, so here's sort of one way to think about it. It's approaching a particular value. Well, let's think about what we could call that value. Let's suppose for a second we call this L. That says, in other words, xn is getting close to L. That's what we have. That's our philosophy. Okay, so what does that say xn plus 1 gets close to? Well, xn plus 1 is right next to xn. See, they're getting close to each other at the end. So if we look way down there at the end, we're like, hello down there, and we look down there, we say, look, they almost all look identical as you get closer and closer to infinity. You know, so as you get further along in the process, the numbers look more similar to each other. So whatever the number is, we'd say, well, look, this xn plus 1 is really getting close to that. So it should be that L should satisfy 4 times L over 5 plus 4 over L to the 4th. Right? Because everything's getting close to L, so this side is getting close to L, and this side gets close to this expression, 4L over 5 plus 4L to the 4th. Well, let's multiply by just enough to get rid of our fractions. Let's suppose we multiply by 5 times L to the 4th. So if we do that to everything, over here we have 5L to the 5th, because we have to multiply by 5 and L to the 4th. Here the 5's cancel. That would be 4L to the 5th. And here, the L to the 4th cancel, plus 20. Well, move this across. We get L to the 5th equals 20. And so L should be the 5th root of 20. All right. And there you go. There's the answer. Now, first off, it doesn't seem very satisfying because, like, what happened here? The second thing that's even more like, whoa, hold on. Where's Nernst's method? I thought this was Nernst's method. What are you doing? All right. This idea will come up again, especially when you see Calculus 2. We're going to have a great time in Calculus 2. It's going to be the best. But this sort of idea is like, well, what happens in the long run? And sort of saying, well, if I know it's behaving to going to a particular value, I can really say, look, let me replace the xn. I'll replace it by something that's close by. In this case, L. It's a nice idea. Let's deal with the second question, which is, how does this have anything to do with Newton's method? And the answer is, if we do it this way, it doesn't really. I just want to show you that if you did it this way, don't feel bad. It's actually a great way to do it. How could we do it Newton's method? Okay, so let's think about what Newton's method says. Newton's method says, okay, now we're into method 2. Right? I said we do it in 2 ways. Newton's method says what? Xn plus 1 is equal to xn minus f of xn over f prime of xn. So what we're going to do is we're going to take our expression here and make it look like that. How do we do it? Well, not so bad. We have the xn plus 1 equals, so currently we have 4/5 xn plus 4 over xn to the 4th. Now, what I'm going to do is I'm going to say, well, this is really xn, and now I'm going to say subtract other stuff. I just have to figure out what the other stuff is. You notice here how I have 4/5 xn. Well, what do I have to subtract from xn to get to 4/5 xn? The answer is 1/5 xn. That's how much I have to subtract. Don't forget you also have this piece, this 4 over xn to the 4th. All right? So because of the minus, it'll become a minus 4 over xn to the 4th. Okay, so now we say, aha, our expression can be written in this form. But let's clean that up. Because I really want whatever I'm being subtracted to be a fraction. So I want to get a common denominator. Well, here the denominator is 5. Here it's xn to the 4th. 5xn to the 4th. Now, in the first term, I have to multiply by xn to the 4th. So that would be xn to the 5th. The second term, I have to multiply by 5 minus 20. So stare at this for a second and ask yourself the question, does this look like Newton's method? In other words, if I'm thinking of this top here as being my f of xn, what I really get is that f of x would be x to the fifth minus 20. What's the derivative of x to the fifth minus 20? Well, it's the derivative of x to the fifth. It's 5x to the fourth. Ah, that's our f prime of xn. And so we have our great aha moment. What's our great aha? Our great aha is that this is Newton's method for our function, namely x to the fifth minus 20. So we say, well, whoops, Newton method for our f of x equals x to the fifth minus 20. And now we say, well, what is Newton's method doing? Newton's method is looking for a root. So it's going to find a place where x to the fifth minus 20 equals 0. Now, when I say find, I mean in the long run. If you kept doing it infinitely often, it gets closer and closer and closer, and the approximations get better and better. Well, that's where x to the fifth equals 20. And now we say, aha, that says I'm going to the fifth root of 20. Same as before. They match. Well, of course they match, because we're really looking at the problem in a couple of different ways. One way says, well, what's the long-term behavior? Let's give it a name. Let's figure out what it needs to be in order to satisfy this type of relationship. The other one says, well, what's the machinery? What are we using to create the machinery? And then what does the machinery say we should be finding? And in the end, we both get the right answer. So it's nice to be able to say, hey, we have options. There's more than one way to do it. All right, well, this was good. Hope you keep practicing. And of course, still more fun stuff to come. Have a great day.